вторую задачу. Как бы третья через вторую. Если рассмотреть весовое пространство веса 0, вот, для ЖЛК, это как раз оно будет, это как раз и будет V с чертой примерно. Да. Вот, ну хорошо. Так, ну хорошо, тогда давайте, Марко, расскажете первый.
Okay, is it working? Okay, let's try it. So first of all, C lambda is A lambda and then B lambda. Yeah, A lambda is sum of E lambda where E sigma where sigma lying in D lambda, and B lambda is sigma. E sigma is it's an element of CSK that represents sigma. Well, it's just such a vector. I suppose usually is writing like that, not just. Okay, E sigma, where sigma is in Q lambda. With sign, yeah. Sigma. Okay, first of all, D lambda is trivial for consists of only identity for T0, since every row has same elements, so it's just identity. D lambda, it's elements of SK that how to say that how to say it. Well, it's in each. It can only.
So the question is,
what is D lambda? I forgot how to say it. What? No, it's Q lambda. Q lambda, it's permutations that permutes elements in columns. D lambda is permutations that permutes elements in row, in each row. And since each row of T0 is consists of same elements, D lambda is identity. I suppose D lambda is such permutations that permutes in row that not equal. Is it true?
No. D lambda is a subgroup in
SK. Yes.
You should write the diagram 1, 2, 3, and so on. And D lambda permutes elements on rows of this diagram.
Yeah, but
so it can change, for example, 1 and 2.
well, if you say something like that, it can change 1 and 2, it can change 1 and 3, it can change 4 and 5. Yeah, but if it's something like this, D lambda then will be equal to identity.
D lambda is an element, is a fixed subgroup of our group SK.
Yes.
It cannot be identity. I think you mean that D lambda acts trivially on T0, but it's not identity, right?
yeah, it's mapped to identity, right?
Yes, but
this image, right, in the action
So yeah, when we say that C lambda, A lambda is equal to A lambda multiplied by B lambda, and we mean that A lambda is as an image of this, yeah?
So d lambda is in the stabilizer of T0.
Yes. Yeah, but I want to understand. So like when we permute T0 by B lambda, it wouldn't be, well, row can be, in one row there can be not equal elements. So after we permute by B lambda, it can be sum of summands will look like this, 2, 1, yeah? And then can we move 2 and 1? Yes? Well, if we, I want to ask what will happen with if we say it's C lambda to 1, 1, 2. What it will be? I suppose it will be something like 1, 1, 2 minus 2, 1, 1. Yes. Is it true?
No, then it is B lambda acting on.
And then we need to act A lambda. And A lambda should apply not trivially. To this it will apply trivially, but aha.
To this,
Okay.
so it will be
Yes, it will be something.
1, 1, 2. Actually,
2 minus 2, 1, 1 minus
1, 2.
1, 2, 1. 1, 2, 1.
And actually 2 here. So you
What?
permute, nothing changes. So
You mean
yes.
So it's like this. Okay, then I didn't complete it. I suppose that A lambda should be like A lambda fixed when we fix T0, and it should be something like identity. Okay.
So when you apply A lambda, yeah. So when you apply B lambda, you kind of go outside of
If we apply something trivial from B lambda, then we, after applying B lambda, can take T0.
Why don't you just motion by
Yeah, that's what we want.
by R?
Uh,
And
why you can by R, but
well, if you
then we will have some just the same T0 multiplied by some number.
yeah, but you don't have this relation.
yeah, but if we
But it proves that even if we quotient out these relations, and we will obtain non-zero element.
Yes. Yeah, you can do this. Sure.
okay, so then it's easier, since
But this only works to prove that it is not zero.
yes, to prove that this is 0, it's not. It's
I
not.
would like to see that it's also not that it is all single.
Yeah, I can't.
So
Я думаю, что там есть, что у нас есть соотношение.
okay, so let me say something about this. So we actually have. So I would like to prove that Eij acting on C lambda T0 is 0. So actually I would like to. So this commutes. So I need to prove that this because actions of GLN and self-escape can be. So I need to prove that this is zero. Right? But in each, so this is the sum over VS's, right? Such that in each S here, we have this young term law, and in each S there at least one row with equal column with equal entries. Yes. So in each S there is there is a column with two equal entries. Now, as was mentioned in Telegram chat, I actually can consider only B lambda.
Why so?
So because B lambda, I can write it like this. It's 1/2 sum over tau from what was notation Q lambda here, right? Negative 1 to the power lambda tau, right? Minus sum negative 1 to the power y lambda. It's tau here. So this is just the definition of B lambda, and I can actually multiply everything here by some 2-cycle sigma. Here tau also runs over. So sigma here is a 2-cycle that permutes two elements of. So I fixed some S here, and say it has like two equal entries in some column. So I take sigma which permutes these two entries. So this is my sigma.
Why it's true? Why this equals?
So because Q lambda is a group, right? And G is G.
Oh, sigma is just
An element of this group.
okay.
But then the sign that appears here is it's negative, right? So therefore I can write it like this, and so therefore it is actually 1/2 B lambda 1 minus sigma. So therefore,
Why don't you have
because this is the same as this. Yes. Yeah, 1/2. Yeah, and so therefore, since I chose sigma like that, right, then 1/2 this thing, so 1/2 B lambda, or actually I can multiply by lambda now, B lambda 1 minus sigma acting on Vs is 0, right? And this is the same as 1/2 C lambda acting on
And we can
Vs. And this you can do. So you actually prove that the C lambda acting on each term here is 0.
I suppose we don't mean 1/2. Like
No,
it's
no,
just
we
C
still.
lambda, it's just C lambda of Vs.
Yes.
Yeah, that's true.
So I think I proved the number whatever. What was the second part, right? So I proved this. So what about?
Yeah, that's all.
But we also need to check that C lambda B is 0 is not 0.
No, I suppose we didn't do it.
So what was the argument?
If we consider action of P lambda on T0,
Mm-hmm.
we will have big sum. Every element of O lambda
Mm-hmm.
acts trivial.
cancel out, окей, yeah.
Сократится со знаков в самой формуле и останется просто сумма. Большого числа d0. Получается у нас...
Ну да, это если мы...
Почему там они между собой не сократятся знаки?
Они все плюсы.
Они все плюс. Ну да.
Потому что только мы меняем 2, у нас же v лямбда, это то, что если 2 равно, то это...
Да.
Лямбда есть только положительное число.
Давайте тогда ко второй переходить. Так.
Denote the representation by row. And we know that the representation of Lie algebra is such a scene. We have some vector v. What is this vector? It is such a vector from v on which all some mu it is some complex number which is independent of k. It is the definition of v0.
I think it's rather some statement.
Yes, yes.
Zero.
Yes, so it is such scene where all E can write such in such way. It is the definition. And we have some sigma in SK and having sigma we can construct an operator in GLK which is it is by definition of inclusion. we have sk here, it includes in such way.
Yeah, so inverse it just takes vi and sends it to v.
Sigma I. And I have to prove that we want to show that if v is in v0, then a sigma v is also in v0. But what does it mean? If I take I want to show that such thing acting on a sigma v is 0 for any k and l. We want to show this, and it is equal to saying that 1 plus rho 1 plus t plus it is we take differential. So what this means, such thing. I only translate this in terms of some t, a tangent vector. So I can multiply by a sigma. Excuse me. We can multiply it by on the left by rho by such thing.
Suppose there's everywhere when you write a sigma is rho of a sigma.
Yes, yes. To be precise. And we can multiply it on the left by such thing. Hence, we will get so I simply rewrite this. And it is equal to here I can write such thing acting on v is 0, but we can easily compute this thing. For example, here we have E sigma L sigma in inverse L. Then I apply such thing, and then I apply such thing, and of course I will get hence this thing is equal to and we already know that it acts by 0 on V by this definition. And we have done. On the second part, I would like to work with the realization of V lambda as C lambda acting on V. We already know this. And this action is permutating of tensor factors. And then what is L lambda 0? I will write. I claim that it is equal to V lambda what I can use this definition, but instead of such thing, I can write that rho, the one rho I kakate on acting on U is some lambda U multiplied on U for K. It is equivalent condition. And here one can see that only such vectors satisfies this condition. So the tensor from here must have each number from 1 to k only once here. We have each tensor here, so I can write 1 it is a weight vector with respect to GLK. And I have to understand which vectors have weight 0. There are such vectors with which have on which IKK acts similarly. So EMM acting on this V is V. It acts by Leibniz rule, multiplying by numbers of M, M1, so if I want that this number is equal for all M, I need that all these numbers are 1 to K in some order. Yes.
There's the only way to make them all equal present in such tensor.
And the action of T here is, if I consider T, tau from Sk included in GLK, notice that it acts in the other way, not by permutation of these vectors, but it sends ei to e sigma I, e tau I. If I want to act by some A in GLK on such tensor, I need to act by A on each vector simultaneously. Hence, tau acting on E sigma 1 and 1 is E tau sigma 1 and so on. And then I would like, yes, because we have from GLK, and then yes, and then I can consider a map from, of course I can consider a map phi from span over C to a group algebra. It sends such vector to sigma. Yes, and it is obvious with this observation that it is a homomorphism of SK modules. Of course, it is an injection, and I would like to understand what is the image of this scene. It is simply V lambda intersects with this yes, I would like to understand what is it. Yes, it is an isomorphism. And I would like to understand what is the image of this scene. Notice that the action of C lambda here isn't as, for example, tau here, because here C lambda permutes factors in a tensor product. But we already know that if I have E1 Ek and acts by Xc on it, some element from SK, and I will get we already know this. This action is in terms of permutation of factors. Hence, C lambda acting on this is B lambda A lambda phi. Because we write here Xc in inverse, and if I write a lambda is sum of sigma, b lambda is sum of tau, na sine tau, and when I apply a lambda b lambda, it is applying sigma tau sine tau. Then here I write such thing. But since all sigmas and all taus forms a group, it is the same as such thing. And it is b lambda, a lambda. And finally, I would like to use some...
So what's written here, actually I can write just C lambda, right?
yes.
And independently you can, for C lambda, you can just switch them, right?
Yes. Hence, I have proved that it is the isomorphism of SK modules. And finally, it is an easy fact that S lambda, which is by definition such thing, it is isomorphic to and it is a really easy fact because I can take here x, we can construct an explicit isomorphism. We can take x here and map it in such way. And we can take y here and map here, and if I consider the composition, it is x to x c lambda. But we already know that c lambda in square is proportional to c lambda. Hence, if I multiply it by a proper constant, I will get an isomorphism. Hence, we have proved that it is C lambda.
But why did you switch B lambda and A lambda in the first place? Why couldn't you just write C lambda here and C lambda here?
No, because we have such action.
Right. Because it's
We have such phi. Well, I suppose we can use phi. Phi will still be isomorphism if
Yes.
we go to sigma minus 1.
No, it is a normal homomorphism. And since we have minus 1 here, we have such thing.
Yes. Did you use the fact that
No.
No.
And how it's supposed to be?
Is-
No, if you didn't, then it's okay, but I just figured that it might help because you have this C lambda, right? So you have so I would like to consider this. because this is faithful, since they are all different, it's just action of this thing on on whatever alphabet in key letters. So this is actually faithful. So this is so this is actually isomorphism of escape modules.
By faithful, you mean subjective?
I mean injective.
Subjective, yeah.
The fact that it's surjective is
It's from the...
it's just one vector, it's just orbit of this vector in here, so it's surjective.
Is the action of permutations on V is a permutation of factors?
Yes.
Yes.
So yeah, on the right hand side it's V0.
So this actually also acts on here as a permutation of
Yes.
factor. So everything is permutation of factor, like introduced in the lecture. So we have this, but this is inside V lambda 0.
Why?
Well, because this is inside V lambda 0.
Yeah, just permutation.
Yes.
So therefore, I just need to check the dimensions. So I gave dimension of this, and I know from our not previous but lecture before what is the dimension of this. You should actually compute all the bases there, which consists of standard Young diagrams, and I need a semi-standard Young tableaus. Sorry. And you need those semi-standard Young tableaus which have weight 0. These are exactly standard tableaus. And so you can compare them, that's it. So I thought in this one.
Why is it weight 0?
Why is this weight 0?
V lambda 0, lambda 0, why it's standard Young tableau?
Because it's weight SLM weight 0, right? So you just compute. So your standard Young tableau is you fill with numbers without repetition, and you have k numbers and k boxes. So each number appears exactly once, and EMN minus ELL gives me difference between number of m's minus number of l's in this tableau, which is 0 because m appears once and l appears once in every standard Young tableau. And if something appears twice, then the other doesn't appear, for example, and then difference is and everything is broken. So if I take something not standard, it will not be in here. But standards are exactly, according to lectures before, gives me exactly basis in V0. So yeah. But apparently you can. That's fine. That was to mention. All right. Very good. So what about the third problem then? So okay, let me maybe just since Nikolai did all the work. Third problem actually should follow more or less easily from the second. Let me read something. So how to obtain sure wave duality from GOK-GLM. right. So so this thing is actually GL. So SK tensor GON model. Okay, so this thing is SK.
We're looking on weight 0 as
Weight
SLK.
0 with respect to
SLK.
action of GOK.
Okay.
Like this.
What
Mainly this is
Is
okay.
it GLK or SLK? Zero.
So 0 is GOK because SK, this K should correspond to this K, as we proved in the previous. So I take GOK.
No, before zero was with respect to SLK.
Yes, okay, actually.
Yes.
And there is GLK.
Yes, that's all. So I need to understand what is this thing and to what does it correspond on the right. So what's written on the, so I need to consider the sum, right? So this GLK, GLN. So this 0 with respect to SLK is exactly what we need in short wave duality, right?
Yeah, but isn't it like obvious since we know that by SLK is just L lambda SLK and multiplied by just
Yes.
numbers. It's just some
Yeah. So
number.
this part is easy.
Yeah.
Right. So it's lambda. Only I need to figure out. So here lambda is all partitions with at most minimum of kn probes. But in short wave duality, lambda should be partition of k. So that's one question that we should decide how. Why do we only live with that? So if I have right, so I need only 0 weight subspace here. Right. So how to explain that? So then, so let me finish writing. Yes, lambda, L lambda, GON. So I actually need the following fact that L lambda if I take L lambda, consider is 0.
Why lambda is a partition of k?
Yeah, so that's what I want. So maybe
Maybe we don't need such thing. We only need that embed v bar in bkn0 SLK and decompose it, and for v bar prove that lambda is a partition of k.
okay. So you said that you solved that right in the list. So maybe it's better for you to explain because I didn't. Yeah, okay, maybe you will explain it better because kind of I didn't think it's true enough how to explain. So what's your? Yeah, maybe we just don't need the partition of k here. We just wonder how to go from to prove sure wave duality. We have decomposition of partitions of k.
I can embed V bar in pkn in a such way. E in such vector maps to and it is easy to realize that phi is a SK CSK tensor GLN homomorphism.
So is it the same homomorphism that we constructed the last seminar slash lecture? We constructed some like
Yes, yes, yes.
but on the seminar we said that it's homomorphism from V bar quotient by M lambda.
No, here the action of such two things are independent. For GLN, it is clear that it is a homomorphism because GLN acts on by Leibniz rule on each of these vectors, and here on this in the same way it acts on these factors, and I claim that it is also the isomorphism of SK modules. And here SK acts by a permutation of factors. But here SK acts as it is a non-trivial statement. So here I can't нет смысла переставлять слагаемые множители. So it is clear, but it is a non-trivial. And then I can, since here we have different first indexes, im phi lies in pkn of degree k 0. It is a representation. Hence I can write for some lambda JL K here I can write such thing and no,
How you actually have only partition of k by taking only
yes,
on the homogeneous of degree k.
yes, and I have such thing, it is pkn k because it is a submodule. I can write this thing and each such thing as also a submodule, JLK submodule, and hence the zero part is JLK acts only on the first factor, hence.
But the summation here over which lambda?
We now suppose that on some lambda.
So we didn't say it yet, right?
Yes.
So here is over some lambda.
Yes. And I have such thing here.
Yes.
Because what is the action of EAA GLK. It maps that IE to that IE, and the eigenvalue of such thing is a number of a's among 1 and so on k, but it is only one a among them. Hence I have proved that it is V bar, and it is the sum of over some lambdas of course all lambdas have partition. Every lambda here is a partition of k, because S lambda is a representation.
No, but we
Oh.
proved this equality only
For partitions of
for
k.
partitions of k.
Oh.
Yeah, I don't know what if it's not a partition of k. I
Oh.
don't know. Something should be said, right?
Oh. It.
So we need to see that L lambda 0. If lambda is not k, if it consists of not k boxes, right? Then L lambda 0 k 0. I would like it to be 0, right?
Oh, of course, partition of k, because the homogeneous polynomials of degree k, and the eigenvalue is a number of a's among first indices, and the amount
Yes.
of one
Yes,
and
very
k's
good.
among
Yes,
first
yes.
indices is k.
So you can act by identity, right? You can act by some I jk, a from 1 to k on here, and actually will just give me a k, right? And so therefore. And therefore, action on each, so it is the same as action on this thing, right? So, and the action of this thing in this representation is exactly this. So therefore, this should be equal to k. And so therefore, it's only partition of k.
А можешь все-таки вот вопрос задать? Вот у нас был Мафин в семинаре прошлом, то, что он там ВТ отправляет в ДТ.
Да, давайте напишем.
Это то же самое, как Мафин, что ли?
Сейчас поймем.
Просто у нас как бы в чем проблема? У нас в семинаре мы доказывали, что V с черточкой фактор по R лямбда это линейный гомоморфизм
любой моном получить степень k.
Да, все вот такие мономы изоморфны, значит, это такое подпроизведение, просто изоморфны в бар. Нет, что я говорю?
Да.
Изоморфны. Да, просто потому что C от Z1, ZN это изоморфно CN, как представление ЖЛ. Вот. Ну нет, изоморфно в бар, вообще-то в сейчас что я хочу сказать?
Сейчас, то, что мы любой моном пятой степени можем получить, это правда.
Можно еще так сказать, почему. То есть какие вот такие мономы имеют вес 0. Те, у которых одинаковое количество единиц, двоек и так далее. Но это в точности такие. Других нет.
Нет, что вот это такое, это понятно, что это как бы все мономы вот такого вида. Это то, что сейчас Николай сказал. С другой стороны, почему все мономы такого вида,
ну почему они получаются?
это ваба. Тоже понятно, да, потому что, я вот это, потому что вот это изоморфно CN, как я и сказал, вот. Соответственно, если у меня есть какая-то переменная ZI здесь, вот, я ее отправляю и она там с каким-нибудь индексом A вторым. Вот. Я ее отправляю в бар как, соответственно, в бар у меня CN, тензор CN, да? И раз. Вот. Я вот этот ZIA отправляю в эти множители. Да. То есть у меня вот это изоморфно просто. На самом деле не совсем так, а вот так. Грубо говоря, это правда, да, но CN тогда изоморфен просто, линейно. C1 всем однородным степень 1. Хорошо. Так, что, четвертый.
Так, что нас там просит доказать? Ага. Да, значит, первая часть. У нас есть, so we have an obvious isomorphism of vector spaces with a linear span of letters Z, A, I. I from 1 to n. It sends, so assume that here we have basis EA, and here we have basis FI. So it sends this basis vector to ZAI. And moreover, it's not just isomorphism of vector spaces, it's an isomorphism of GLK. Okay. No. Yes. U of GLK tensor U of GLN modules. So it's very easy to check. And then we just take their symmetric powers. Here we have a symmetric power of CK tensor Cn. And here we have symmetric power of this, which is just a ring of polynomials. And action of GLK and GLN to the symmetric power is extended by the Leibniz rule, and action here is by vector fields, so it also satisfies Leibniz rule. So this is isomorphism of representations. Okay, differential operators of first order. It's vector fields. So the first part is done. The second part. Yes, now we need to prove our GLK duality. So let's start. We have our PKN, which is isomorphic to this, and we write it as a direct sum of these symmetric powers of CK tensor Cn. Then we use isomorphism from the list and write that this is we need to take CK to the dth tensor power and tensor it by Cn to the dth tensor power, and then take invariance by the action of symmetric group SD.
So it acts on just diagonally.
Yes, diagonally. It permutes elements of tensors here and here. Okay, then we can what we do next? Next, we use Schur-Weil duality for this module and this module. This is GLK module. This is GLN module. So it's direct sum over all D mod 0. Apply Schur-Weil duality. Sum over all lambdas such that it's a partition of D and no more than k rows. Here we have S lambda corresponding to the symmetric group SD, tensored by L lambda corresponding to GLK, and tensor it by the same thing but for GLN. Here we have mu, again it's partition of D and no more than n rows. we again have Specht module for SD, and the L lambda we have for GLN. And we need to take invariance. Now we can use properties of tensor product and direct sum and say this is a direct sum over d more 0, and here we have direct sum over lambda and mu with that properties. Of what? Of S lambda d tensor S mu d, and here, and we can put invariance here because SD acts only here and here, and then tensor by everything else, L lambda k and L lambda L mu. Yes, L mu n. Now we need to compute this, and this can be done by properties of these Specht modules. Okay, I will forget about this letter D. S lambda tensor S lambda SD invariance. What is it? Firstly, we know that S lambda is isomorphic to S lambda dual, so it's here we have S mu. S lambda dual tensor S mu SD invariance. So this representation is just home from S lambda to S mu, and take invariance, which is home over SD. And by Schur lemma, we know that this is delta lambda mu. I see. So the only way for this thing to be non-zero is when lambda is equal to mu, and otherwise it is just C. So this direct sum is a sum over OD over all lambda, HD. So for this lambda we need that it so this lambda must have no more than k rows and n rows. So the condition for rows, and here we have this lambda k tensor L mu n, and we're done. Just direct sum over all lambdas with condition for rows L lambda of k tensor by L lambda of n.
Считаю, можно и на сессии пару провести.
Нет, ну если вы хотите.
Да можно все лето пары проводить.
Нет, ну это... Так, нет, ну давайте план такой, что...
Окей, ну следующий, ну 2 лекции еще, да? Окей.
Да.
А мы сегодня бесконечно нервные, да, вот будем.
Ну что-то, да, такой, типа, быстрый, какой-то, что-то скажи.
Ну не диаграмму будем продать.
Не диаграмма.
Точно.
Где эта книжка?
Это правда.
А кто? Чё? Чё я не знаю?
Понятно, спасибо.
Где тестовый вариант
Сейчас
книжки?
Книжка находится у Нины Владимировны,
Ага.
Галины Пугачевой, потому что она ленилась. Но ей она звонила начальству и сказали, что вот делиться со студентами нельзя, но можно спрашивать все, что хочется спросить. Спасибо.
А из вас кто-нибудь собирается сейчас, на следующий год, ну, наверное, как минимум 2 человека, да, остается?
А, у меня
Николай
на третий
или-
курс, да. Николай вроде второй.
Ну, я остаюсь,
А, вот.
но в магистратуре.
А, ну, там просто будет вот этот курс по фильмам.
По фильму «Алгебра в конце».
Да.
Ну, это...
Интересно, кстати, собирается?
Пока нет в списке курсов. Непонятно вообще, что будет. Там, ну как, есть просто название вроде на сайте.
Ну, да, название есть на сайте. И еще есть ну, преподаватели. То есть название преподавателей, количество предметов, есть вот такое. Есть такая ссылка.
Ты книжку обещал отправить.
Нет, ну это не книжка, это вот это вот. То есть там нет ничего.
То есть аннотации нету, да?
Да, то есть аннотации никакой нет, скинуть.
Да нет, это я видел.
Окей. Ну, то есть, да, просто там только эти... И преподаватель, сам название курса и книжка. Ну и вроде сколько времени будет в неделю. Ну, то есть чисто все без аннотации, без того, что будет. Да, если еще если подумать, то вот этот вот курс в следующем году будет называться по-другому. А
Да,
это что можно взять?
А я, кстати, думаю, сейчас вот этот про информацию.
Ну, вот этот курс сейчас, это группа алгебры.
Да, он будет называться структурная теория, кажется,
Да,
да?
структурная теория алгебры.
Что-то я как-то думал, да. Но я думаю, что я по-любому, ну, ну, не все, конечно, но я вот думаю, что после того, как значит, закончить структурную теорию, что там по классификации можно сказать побольше там всего. Вот. А потом как бы идти скорее по книжке Хамфриса к истории его. Ну, а там много повторяется, по книжным мерам, там прям то же самое все рассказывается, только в рамках, ну там больше слова к истории его. А потом там можно дальше какие-то более технические вещи, чем прям ГГ.
А я слышал, что вся эта там, классификация этих алгебр Ли, она как-то связана с элементарными частицами. Причем напрямую.
Не знаю.
Не
Я
знаете?
никогда не слышал. Я учился на кафедре физики элементарных частиц. Я как бы это не слышал.
Ну,
Ну, в смысле, там всякие эти, там, как здесь, я уже забыл, если честно. 3 поколения, да, вот,
ну вот
поколения
что такое,
частиц,
да.
вот это все. Да нет, там же максимум какая-то алгебра Ли, которая влезает, просто такие небольшого ранга, какие-нибудь S1, S2. Вот, это всякие преобразования между поколениями. Это как раз складывается.
Ну не знаю, я так. Только вот фразу слышал.
Классификация этих.
Откуда вообще все эти алгебры Ли физики возникают?
Ну, есть там всякие, есть контрольные теории поля. Там как раз нужны афинные алгебры. Это, ну, вот это некое бесконечно мерное обобщение простых. Это то, что в современной физике делается. А так, ну да, там всякие есть симметрии. Ну, я не знаю, спиновая модель, это всякие какие-то представления SL2 в каком-то смысле. Вот спин 1/2 это
хотя бы такие базовые.
Ну, а так современное применение, это, конечно, это бесконечно медленно. Ну, и есть еще одна классификация не афинных вот этих смузи, а есть классификация там векторных, ну, алгебры вообще векторных полей. Тоже картан сделал.
Но они большие какие-то, нет?
Ну, там классификация, по-моему, похожая на то, что для полупроцессной инженера. Ну, я не знаю, я так тоже какие-то слова читал, но что-то изучал. Но это тоже как бы имеет отношение к физике, потому что там
Многообразие какие? Гладкие, комплексные или
ну, гладкие,
алгебраические?
по-моему, вещественные даже. Вообще, когда, сейчас, если у меня есть, ну, с вещественным, там, у меня же есть алгебры, которые соответствуют компактным формам. Есть компактные формы, есть там сплит формы. Это тоже известная классификация. Вот. Так что...
Мне просто кажется, что вот если есть многообразие, то векторных полей на нем прям очень много. И там какой-то... Как-то странно, что есть какая-то классификация.
Даже есть там аналитические проекты. Ну да, понятно.
Нет, ну они, это что-то там бесконечно мерно. Вот,
Нет,
нет,
это
какой там...
окружности же там просто...
Ну, в каком-то смысле это, да, их не так, ну да, на окружности это то, что называется афинная космуза там, для SM2, в каком-то смысле, когда вы берете там. Ну да, вы берете вот такую. Ну, мы сегодня что-то посмотрим такое. То есть многочлены Лорана со значениями там в алгебре. Ну, и вот так, ну, это как пример афинной космологии. Ну, в смысле, это и есть. Ну, как бы, это где надо там центрально расширить, там еще добавить какой-то там оператор, который за градуировку отвечает, вот это будет афинная космология. Вот. И таких, ну, есть как бы классификация. Ну, в смысле, нет, понятно, что их не больше, чем у простых. Вот. Нет, я могу как бы к ним прийти из, ну, просто обобщая картанную матрицу. А как к таким, какие матрицы то встретим, ну, это вот известно. В этом смысле есть классификация. Но это на окружности как раз.
На окружности. Сейчас откуда тут окружность? А, типа это Т?
Т и Т в минус первый. Это, значит, у меня есть и фи.
Да. Понятно.
Okay, let's start. So first, I would like to introduce what are Kac-Moody algebras. So the goal is the following: to introduce something that arises if you would like to invent something infinite dimensional, but with the same structure. So it's Kac-Moody algebras, and then to consider like the simplest but very rich example is SL2 affine. So how it's related to Kac-Moody and why it's Kac-Moody algebra, and actually what new features we have for this infinite dimensional case. So again, let me start with some definition. So let me consider square matrix n by n with complex entries, and I say that so a realization of this matrix is a triple. It consists of the following triple: H, pi, and pi check, where, well, H is finite dimensional vector space, pi it is some set alpha 1 alpha n, and here the same as here. It is inside H star, and this is linearly independent subset. Linearly independent subset. And then pi check, it's a subset in H now, consisting of the same number of elements, and it is also linearly independent. Subset. And we have some relation between pi and pi check, so such that if you take alpha j, compute on hi, this will give me a ij. So what I would like to stress here is that dimension of H is not necessarily n. So here, this definition of realization of square matrix. We'll need some estimate on dimension of H that we can have. So lemma, if H pi check is a realization of A, then dimension of H is greater or equal than 2n minus rank A. It's easy to prove. So proof. So let me consider matrix alpha j of hi. So this is an element of my matrix. Right, and sorry. First of all, I would like to complete. Sorry. So let me erase that. So of course this matrix is just A, but I will take my pi and pi check and complete it two bases in H star and H. So complete or extend pi and pi check to bases alpha 1, alpha m, and H1, HM of H star and H respectively. Then I consider matrix alpha J of HI. Right, so here IJ from 1 to M. It looks as follows. So in the upper left corner you have A and then other blocks. A, B, C, D. Where this A is the matrix that we started with. And it is inversible because this abasis is invertible. Because if it's not invertible, this abasis. Yeah, so if it's not inversible, then there's linear dependence on alpha or H's. A is just 0. Sure. So what's the problem? Okay, so let's continue. Okay, let me go here. Then I just consider this matrix, but only upper half of it. So I have A, B. This is not square, it's rather rectangular, but it has rank, which is, number of rows. It has rank n. So actually, I can choose n linearly independent columns in, I don't know, let me call this A tilde, for example. And n, then I can write as a sum n1 and n2, right, where n1 is the number of columns that I chose in A, and n2 is the number of columns that I chose in B, right? Columns in A, this is columns in B. Very well, and so n1 is then less or equal than rank of A, and n2 is less or equal than rank of B, of course. Right. On the other hand, rank of B, so B is m minus n by n. Right, so rank of B is less or equal than n minus n. On the other hand, it is greater or equal than n minus R, right? Because, well, I can rewrite this. N is less or equal than rank A. So rank A, let me denote it by R. So N is less or equal than R plus rank B. Right, so therefore rank B is greater or equal than N minus R. And so that's what I wrote here. So therefore I have M minus N is greater or equal than N minus R. So therefore M is greater or equal than 2N minus R. And this is exactly what we needed. So R is rank, 2N, M is dimension of H. R is rank of A. On the other hand, so we proved lemma. So the question is whether we have, whether we can achieve equality there. And so the answer is yes, we can. And let us actually invent a name for this situation. So definition, if dimension of H equals to N minus rank A, then realization is called minimal. Proposition for any A there exists a minimal realization. It's also easy to prove. I don't know if we, okay, so it's a couple lines. So without loss of generality, I can say, I can think of A as consisting of the following blocks. A11, A12, A21, A22. A11 is R by R, and it is so determinant is of A11 is not 0. So actually I can permute rows and columns if I found minimal realization for some A with permute for new matrix with permuted rows and columns. Then I found a minimal realization for initial matrix, right? So therefore I can assume that I have this block here. But then I can define C to be such matrix. A11, A12, A21, A22. And then it has two more, so one more row and one more column of like block, row, block, column. So 0 identity of the size I minus R here, identity of the size I n minus R here, 0, 0. But then determinant of C you can see just, you know, by expanding maybe by these columns, is just plus or minus determinant of A11. So it's not 0. And then I would like to take the following. I would like to take H1, Hn to be the first n rows of C. Of C. So this will give me some basis in n-dimensional actually. So the size of this is 2n minus r. Is 2n minus r dimensional space. This will, so first n rows in this matrix is linearly independent vectors into n minus r dimensional space. Okay. On the other hand, I can take alpha 1, alpha n. So these are in C to n minus r. So then these are in the dual space, C to n minus r dual, to be just a basis which is dual to standard basis. To be, it's not a basis though, but this is the first n elements of standard basis in Cn to n minus r star. So dual to E1 En in C to n minus r. So if I take something like this, then this will be minimal realization. Then alpha I computed on Hj is exactly corresponding entry in A. They are linearly independent, both of them, and the space H is 2n minus r dimensional. Okay. So now the construction. So okay, so we had Cartan matrices. Let me introduce what's called generalized Cartan matrix. Definition. Generalized or let me start it like that. A is called, so it's again n by n matrix, is called a generalized Cartan matrix if the following conditions happen. First, on diagonal I have 2's, so this is for all I from 1 to n. Then off diagonal elements are less or equal than 0. So if I is not equal to j. And third condition is if Aij is so Aij is 0 if and only if Aj is 0.
So our matrix is real.
Yes. you're right. This is the most general thing that we can actually require from what we would like to have for generalized Cartan matrix, because we would like to. So we have some matrix, and we know how to obtain like a relations, like cell relations out of it, right? And in particular, so this 2 means that we would like to have SL2 triples in our generalized Lie algebra. Then these conditions say that in the project we would like to have conditions like that. Add 1 minus Aij fi fj equals to 0. So in order for this to make sense, I would like this to be non-positive. We will not have these conditions actually in the definition of Kac-Moody algebra, but these conditions will be there. And this also follows from this thing, because I mean, if my Aij is 0, then fi and fj commute. So therefore, fj and fi commute. Yes. So let me. So okay, now let me take a generalized Cartan matrix. So let A be an n by n generalized Cartan matrix. Then let me take its minimal realization. H pi check be a minimal realization but actually it's unique up to some natural isomorphism of A. And then so let me define first Lie algebra L tilde of A. So let L tilde of A be the Lie algebra with generators EI and Fi, where I runs from 1 to n. And also H. So this is the generating set. And relations. So I actually give you infinite number of generators in a sense. So relations are like that. Well, I have H, X, and Y commute for all X and Y in H. I cannot now only write this with HI and HJ because I have more than, just H is more than span of HIs. No. All right. And then, so I actually would just give you all relations that I have in Serre theorem, except this these hard relations. Okay, all easy relations. What else? I have EI Fj equals to 0 if I is not equal to j, and EI Fj if EI Fi is Hi. This is for all I from 1 to n. And then I have the following. So this is, yes, Hi is an element of pi check. So we have realization of A. It is a some subspace H. It's a bunch of alphas and bunch of HIs. So this HI is from here. And alphas I need, of course, for the following relations. HEI, if I commute, I will get alpha of alpha I of HEI. And if I commute H with Fi, I will get negative alpha of H Fi. And this is for any H from H and I from 1 to n. So this is it. These are all relations that I have so far. So this is a big algebra. But instead of adding these relations, I will do something else, which is a standard thing when you introduce Cauchy-Moody algebra. I'm going to quotient by some ideal in this L tilde. And this will make things much easier. When you're proving theorems, or like just proving that something is Cauchy-Moody algebra, for example. Okay, so it is this one is infinite dimensional.
How you see it? Is there some commutator that there with you?
Yeah, I think so. If you take just if you just take E1. Yeah, it's yeah. If you apply E2, you can try to apply E2.
There's nothing else done.
Yeah. So it's still still not clear, right? Something should be, but I think this one will be. You'll have infinite number of those. No, when I say relation generators and relations, I start with free Lie algebra, which has already Jacobi identity, and then I impose more. I quotient by ideal, which is generated by some elements like that give me. So when I say by generators and relations, I already think that Jacobi identity is there. No, because what I take free Lie algebra, which is on this generating set. But then I can if I have an ideal inside this Lie algebra, I can quotient by it and get another Lie algebra. So I just take an ideal which is generated by elements x, y, and everything which is, and brackets with this one. And also by EIFI minus HI and so on. Yeah, so I think. So the question is how to construct free Lie algebra to have Jacobi identity. Well, we never discussed it, but I mean, there is such construction. Some question? Okay. Very well. So this is my L tilde of A. Now I would like to quotient by some ideal. To get this ideal, I first notice that L of A admits weight decomposition with respect to its commutative subalgebra H. Okay, let me take now this one. L of A is a representation of S representation of H admits weight decomposition. In other words, I can write L tilde of A as a direct sum over some alpha from H star of L tilde of A alpha, where L tilde of A alpha, well, it's clear what it is, right? It's X from here such that Hx equals alpha of Hx for any H from H. Okay, is this lemma clear? I think it's kind of obvious. So let me still write. So you have generators. All generators are weight vectors, right? So EI, FI, H. So these are weight vectors. But then when you apply commutator with EI, right? So if you take L of A alpha, apply, say, EI. Well, so should say add EI. This will be inside L tilde of A of alpha plus alpha of alpha I, yes. And if Fi replaces, so if I have Fi here, I have minus here, right? And if I have H, some H here just does nothing.
Yeah, but I suppose that we didn't prove this lemma.
I didn't, but it just follows from, it's like we checked that a couple of times already.
Yeah, so it's because they all commute H.
Yes, they commute. Yes, you just use commutation relations that we introduced, and this will give us the following. So this proves that. So each, like, of course, you have like a spanning set here, which is words in E, F, or elements of H, right? And each word is a weight vector. So therefore, we have weight decomposition. But then we use, so H is a subalgebra in LA, and it is also finite dimensional. It's okay, right? So and we proved in the seminar that if I have some finite dimensional commutative Lie algebra and some maybe finite dimensional representation of it, then any sub-representation also can admits weight decomposition. So therefore, any ideal in L of A also admits weight decomposition of H.
I suppose we prove it not only for finite dimensional representation.
Yes, yes, yes. That's the whole point. We proved it for finite dimensional H, but L of A can be infinite dimensional. Yes. So therefore, so corollary, any ideal of L tilde of A admits weight decomposition. Okay, so next lemma. Next lemma is that, okay, we had lemma 1, now lemma 2. L of A tilde contains, has an ideal, has a unique maximal ideal that intersects trivially with H. Okay, how do I would like to put it on board? Has an ideal I such that I intersect H is 0, and for any other ideal J such that J intersect H is 0, we have J is inside I. Proof. Again, this technique we already saw a couple of times. So let me take take J. So consider J such that J intersect H is trivial. Then it admits weight decomposition. And here alpha is not 0. Okay, is that clear? So here, this is weight subspace here. So this is just because L of A tilde 0 is H. Well, we have weight decomposition, and we have right. So we have words. Is it obvious? Suppose that, yeah, in my I have words, And I know that, so these are words in E, like F's and H's. So it is in, so this word in here, right? If I have in the word equal number of E's and F's. So the question is whether I have or don't have, whether this is in H. Yeah, this is true. I wanted to avoid the statement just to. No, it's not trivial. If I have some mix E, like F's and H's, some commutators like, I don't know, and then F again, and maybe like a huge word like this. How is it true that you can write this? So what you're trying to say is called triangular decomposition. So I have subalgebra which is generated by E's, subalgebra which is generated by F's and H, and my actually L of A, L tilde of A is direct sum of these three subalgebras. But this is, I mean, this should be proved. I don't know. I don't think it's obvious. But what is easier to see, I guess, is that if you have in a word equal number of F's and E's, then it is generated by H's. So this is in H. If so, this is a number of E's equals to number of F's. Of course, we can prove triangular decomposition. You take this, replace it with. So what do you say? Take this, replace it with one symbol. Yes. Sure. But then you replace it with. No, it's not. It's not clear why you can have E1, E2 again. Yeah, you cannot replace it with one symbol.
That generated by E.
So sorry. So if I have something like this, F3, E1, E2. Yeah. I can use Jacobi addes. Yeah. Then if I have 4, if I have 5, yeah, something is.
No, I suppose we want to say that if there is something that generated by E's, its action by F and H similar to action by E. So it's some constant to this element. Or just
I don't know. I have a proof of triangle decomposition, but we can either believe that this thing, or we can prove things. But this will make us slower, of course. But let me see if I can explain why this is true. Equal number of F's and E's. Yeah, I mean, yeah, induction plus Jacobi density, but still. Yeah, okay, so let me try to prove triangular decomposition for this thing then. To be completely honest, so yeah, okay, this is something that should be checked. Where should I go? I should go here, and then we continue with this one. Okay, so let me introduce n minus, n plus, n minus tilde. So n plus or n, so okay, n plus is subalgebra of L of A tilde generated by EIs. Then n minus tilde, it is the same but generated by FIs. So I here, so from 1 to n, Fi is I from 1 to n here. Then of course n, so then I have another proposition which says that L of A tilde is n plus tilde plus h plus n minus. Okay, so let's prove this. So I would like to claim the following. So claim. Suppose that, so if a subalgebra L of L of A is contains all generators, EIs, FIs, H, and it is closed under taking adjoint action, so at EI, at FI, and at H as H and H, then L equals to L of A. This is a trivial statement.
Said that it closed under adjoint action, isn't it? What subalgebra means?
Sorry, not subalgebra, vector space. Yes. Vector space. So this is not subalgebra. It's a rather vector space inside L of A.
So isn't when we say it is closed under this action? Okay.
Right? So I take generator, start applying this. So I actually generate everything, but never go outside of this space. So this space is everything. So nothing is said here. I just claim something. So I just need to prove. So this thing is a vector space. Oh, contains generators. So I just need to prove that this is closed under action of these three things. Okay, then I proved the proposition.
Isn't you should prove that n plus tilde doesn't intersect h, doesn't intersect n minus tilde?
It is clear because h is inside L0, This is inside not L0. So when you it's just this is inside. Yeah. So this are in different summands of weight decomposition. So they do not intersect. So this one is here. So I just need to prove that. So need to prove that n plus h plus n minus is closed under at EI, at FI, and at H. Okay, let's prove this. To prove this, let me, so okay, I already said what is a word, right? So let me just consider W. It is a, it's a word in Fs only. So let me take W, just some word in Fs. Fi, F, I don't know, I1, Fi2, and so on. And here I have Fi, I don't know, L minus 1, Fil. So this number L here, I also will write L of W. I will say it's length of W. Okay. I would like to prove that want to prove that add x of W is inside H plus n minus tilde. Here x is EI, Fi, or x is in H. By induction on L of W. So let's do this. So base is when L is 1, and this is just follows from commutation relations. So just take and see that it's always in here. So it's just consists of one F, one generator, and you commute with all these things. It will be in H plus n minus. It will be again either n minus, either F again, or in H, right? If you commute with EI, for example. Commutation rule. Base is follows from commutation relations. Step is also easy because you take add x of W, but W is always a commutator of two other words in F. Well, I put brackets like that, but I actually could put, these brackets might be in different order. So it's not like that. It's just some other. So the first bracket can be somewhere in the middle, for example. But it always the last bracket is a commutator of other two words, right? So it's add x of w1, w2. So here length of w1 and w2 is smaller strictly than length of w. Then I use Jacobi identity, so it's add x w1, w2 plus w1 add x w2. So by induction assumption, this is in h plus plus n minus tilde, right? This is in h plus n minus tilde. And therefore, the whole thing is in h plus n minus tilde because, well, this is in n minus tilde, but length is smaller than w. Therefore, h with this is in h plus n minus tilde. This n minus tilde commutator with something from n minus tilde is in n minus tilde, and still in here. So therefore, the whole thing. So therefore, add x of w is inside h plus n minus tilde. And then similarly, you prove that word in is inside h plus n plus tilde. Just similar argument. And this proves everything. It proves that this direct sum is closed under action of these three things. And so therefore it's the whole L tilde of A. Okay? So therefore I proved triangle decomposition, and therefore this one is clear now. Right? So let's continue with proof of this. But then I can take, so what I'm proving? I'm proving that there's an ideal J that is such that it's a unique maximal ideal with this property, that it intersects trivially with H. So I take any ideal with such property. It has a decomposition like that without zero weight subspace. So therefore, I can just take, can take I to be sum over sum of all such J's. So this is just sum of all ideals with this property over all J such that J intersect H is 0. And then of course I intersect, so then I of 0 is 0. It means that I intersect H is 0. Right? And so therefore, I is the ideal that we need. Again, I cannot, I guess, make this conclusion without triangular decomposition, but I do have it. No. Okay. So therefore, I have this unique maximal ideal such that it intersects with H trivially, and I would like to quotient by this ideal. Okay, let me go here. I am completely confused about that. Okay, let me go. So now, finally, I can define what is Kac-Moody Lie algebra is. So definition. Now I take L of A. It is quotient of L tilde by I. So this is called the Kac-Moody Lie algebra associated with A or corresponding to A. And we already have a bunch of good statements. In particular, we have L of A admits weight decomposition. So L of A is direct sum of alpha in H star, L of A alpha. Just because L tilde of A has weight decomposition. So then L of A also has. So because of that, we can define roots. So I can define R to be those alpha from H star such that L of A alpha is not 0. And I guess H star without 0 here. So this is a root system of Kac-Moody Lie algebra. What else can we do? We can actually, since we have now triangular decomposition. So before, okay, we had the roots, and we had the polarization there. So polarization we chose just by choosing a plane, right? But here, and after that, we chose like a simple roots and stuff like that, right? But here we already have simple roots, which are alpha 1 and so alpha. So therefore, polarization should be chosen like corresponding to that. So, and do we have actually positive and negative roots? So we do, because now we have triangular decomposition. So actually, so I have n plus or n minus respectively is inside L, okay, direct sum. So also some things that we can summarize out of all that we have. So L of A alpha. Here alpha runs over some set R plus or R minus. And R plus or R minus is all alpha in R such that, well, it is a span of Ni. It is in the span of alpha i's. And here Ni is greater or equal than 0. Or in case of minus, it's less or equal than 0. So this one is obvious that n plus and minus is inside. such sets, right? But then triangular decomposition says that okay, so let me go upstairs. And plus and minus, yes, these are in the image, yes. Да, да. То есть у нас на самом деле все корни, они лежат ну вот в span of pi. Да. Они все вот такие, да. У нас сначала альфаиты есть, потом мы когда генерируем, у нас к ним еще начинает прибавляться альфаит или вычитаться. Но так как у нас есть теперь треугольное разложение, на самом деле, so by triangular, so since